Welcome to section 11.1 chi-squared goodness of fit tests. So what I'm going to cover in this video is going through the four-step process, talking about the chi-squared distribution, and being able to do a chi-squared goodness of fit test. So if we take a look at this example, this is just talking about candies. We could look back at like chapter 9, what we did, a one proportion Z test, where we were just looking at one specific category of a categorical variable. What a chi-squared goodness of fit test does, it looks at the entire distribution. So instead of just looking at the proportion of one color, we'd be looking at the proportion of all of these colors. So you're not going to see me do this in class. You could write the hypotheses in symbols and just attach the correct proportion to the correct category. Or you can generalize it, which is what you're going to see me do in class, in terms of words, that the entire distribution is as stated for the null hypothesis, and the alternative that it's not as stated or not correct. So there's two main types of counts that you're going to have. You have what are called observed counts, and that's what actually happened in your sample. And you have expected counts, which are based on the distribution that they gave you. So in this case, they said 24% of all M&Ms are blue. So if I take my total 60 times P, N times P, I'm going to get the expected amount of blue M&Ms. Most cases, the expected counts will not be whole numbers. Do not round them. It's just what you would expect to have happen. Observed, that's what happened. Those are going to be integer values. Your test statistic, we have z-scores and t-scores that have been our test statistics. Now we're going to have something called a chi-squared test statistic. The formula for that is the sum of the observed minus the expected count squared divided by the expected for all the possible values. This formula is on your formula sheet. If we take a look at it for this example, you're going to take that 9 minus the 14.4 squared divided by 14.4 plus 8 divided by minus 12 squared divided by 12, and so on and so forth. The reason we're squaring, because we're summing up these differences, I need them to have a positive value. Otherwise, you'd sum them up and they'd end up at 0 every time. So when you sum these up, that's going to give you your chi-squared test statistic, in this case, 10.18, which is not the same as like, oh, your 10.18 standard deviations above the mean. That's not something that it has in common with Z and T test statistics. Okay. All right. At this point, why don't you read through the check of understanding, pause the video, do parts 1, 2, and 3 on your own, then come back and take a look at me going over it. So this is talking about M&Ms again. State the appropriate hypotheses. So the null hypothesis would be that the company's claim about the color distribution of M&Ms is correct. The alternative would be the company's claim for the color distribution of M&Ms is not correct. All right, for the hypotheses, we're all set there. Now calculate the expected count for each color. Well, we have a total of, let's see, 12 plus 7, 19, and 17 is 36, 46 M&Ms. And I'm just going to take 46 times 0.23 for the blue and the orange, 46 times 0.15 for the green and the yellow, and so on and so forth. And that's going to give me these expected counts. As I mentioned before, do not round these. They are what they are. Calculate the chi-squared test statistic. That now comes from doing the observed minus expected squared divided by expected. So for blue, it would be 12 minus 10.58 squared divided by 10.58 plus, for the orange, 7 minus 10.58 squared divided by 7 plus, and so on and so forth. I don't know what that is off the top of my head, but you should see it here. Okay, 11.37. So at this point, you should feel pretty comfortable with the hypotheses, how to get your expected counts, and then how to use those to get your chi-squared test statistic. All right, so this is based on a simulation. And you can notice pretty quickly probably that the chi-squared distribution, this is not approximately normal. So chi-squared distribution, they're skewed to the right. They only take on non-negative values, so 0 or positive, and it's still a density curve. The area underneath it is 1. The degree of skewness is going to decrease. As the degrees of freedom increase, the curve is going to become less and less skewed. So going from the black to the red to the blue, you can see the skewness decreasing. The degrees of freedom are calculated by the number of categories minus 1. So for the M&Ms, I think there was 6 different colors minus 1. There would be 5 degrees of freedom. And just a little review, if the distribution is skewed right, the mean is going to be bigger than the median. So to get our p-value, we're going to be using chi-squared CDF from the test statistic, in this case 10.18 to infinity, comma, 5 degrees of freedom. So similar to TCDF, it'll reference some table in the back. We're not going to use the table, so you don't need to worry about that. All right. Okay. So in this previous one, I'm just going to kind of go through this, confirm the expected counts are large enough. I don't remember it saying that anywhere here. The expected counts have to all be at least 5. At least 5. That's going to be one of our conditions. So in the previous one, all those expected counts to 10.58 and the others are at least 5. Your sampling distribution is going to look like this. You have your test statistic of 11.37. There's not going to be any two-tailed test for chi-squared. It's always going to be shading above the test statistic because we have non-negative values, because we're squaring those differences. And then to get your chi-squared CDF, it's going to be under second vars. So in this case, I'm going to do chi-squared CDF from 11.37 to infinity with 5 degrees of freedom. We're not going to use that table in the back of the book that they're referencing, so this one should give you 0.445. And then what conclusion should you draw? We're going to reject the null because the p-value is less than alpha. So we have convincing evidence that the color distribution for our M&Ms is not what they said. Okay. Pardon my yawn. All right, getting into the actual test itself. We already did the state step earlier with the hypotheses. The plan step, 3 conditions, as always, random, 10%. Large counts, we're back to counts because we're talking about a categorical variable, but we're looking at the entire distribution. So now this is not going to be 10 with like n times p. It's all the expected counts are at least 5. All expected counts are at least 5. All right. There's the hypotheses. Basically, the null hypothesis is the distribution is correct or as stated, alternative being it's not. We talked about that already. Okay, so if I run through this example, this is actually an example in the lesson. It's basically, does the birth date of NHL players have any impact on, is there evidence that the birthdays of NHL players are not uniformly distributed throughout the year? If you remember that term uniform, that means equally likely. So the evidence is for the alternative. So that's the alternative. The null would be that they are uniformly distributed, the distribution of NHL players' birthdays. Random, large counts, 10%, test statistic. All of this is what it is. To get your p-value, chi-squared CDF from that 11.2 to infinity with 3 degrees of freedom gives you this p-value of about 0.011. Conclusion is as it's been. So one thing that we're going to talk about here is how to do this test on the calculator. The observed counts have to go in list 1, the expected go in list 2, and then you're going to bring up a chi-squared GOF test under the stat test menu. You're going to look for chi-squared GOF, and then you'll run that. When you do run that, you're going to get something that spits back at you called CNTRB, or contributions, or components. And what these are, they represent each individual sum. So in the hockey question, we had 4 different categories. January through March, the test statistic was 11.2, out of which, I'm going to make this a little bit bigger, out of which the January through March contributed 7.2 to that. The next group of months contributed 0. the next group 0.8, and the last group 3.2. So I can see the majority of the reason my test statistic is 11.2 is the January to March players. And that's going to come into play when we do what's called a follow-up analysis. Anytime you reject the null hypothesis, you need to do a follow-up analysis. And that's essentially talking about why did we reject the null? In this case, there was a lot more players observed during this period, January through March birthdays, than we expected there to be. And that contributed the most towards my 11.2. Okay, so moving on, I think that might be pretty much it. Summarizing, chi-squared goodness of fit test, you're going to look at the observed counts versus expected. You're going to calculate your test statistic using that formula. Your conditions, random 10%, large counts, but large counts is now talking about expected values, all being at least 5. And then we talked about chi-squared CDF using that. And you need to do a follow-up analysis if you reject the null or if your results are statistically significant, and find that largest contribution or component to the chi-squared test statistic. So I hope this video was helpful for section 11.1.